Now we're going to cover program loaders. Program loaders are small programs that allow the operator to input other, more complex programs into PDP-11 memory. This section of the study unit is divided into 4 areas. First, we will discuss the purpose of loader programs and introduce you to the Bootstrap loader. Following this discussion is an overview of the Bootstrap program. Next, we will explain the operation of the individual instructions that make up the Bootstrap. Finally, we simulate actual running of the Bootstrap program. Let's begin by explaining the purpose of loader programs as well as how they're used to input information into the computer's memory. Programs may be either homemade or ready-made. Homemade programs, as we saw in the I/O programming section of this unit, are developed by the programmer for his specific application. Ready-made programs, on the other hand, are supplied with the system. With each PDP-11 system, the user receives a complete, ready-made paper tape software library. The standard paper tape software library includes programs that allow you to assemble your own programs, to edit these programs, and to perform online debugging in order to check out these programs. Other paper tape programs are furnished to help you perform memory dumps, to simplify the writing of I/O routines, and so on. Before these programs can be used, they have to be placed in memory. However, the computer's memory, when first installed, is completely blank. The computer doesn't have the capability of accepting programs stored on paper tape. How is our first program inserted in memory? Since memory is blank, we have to manually insert a small preliminary program. This program is called a loader. We can deposit this small loader program using the switches on the PDP-11 console. Once this loader program has been placed in memory, the CPU has the capability of bringing in other more complex programs into its memory. Thus, loader programs play a vital role in any computer system. Without these programs, the PDP-11 system could not bring itself up to an operational condition. In this study unit, we will describe 2 loader programs, a Bootstrap loader and an Absolute loader. Why 2 loader programs? The answer is simple. Since the Bootstrap program must be toggled in by hand through the switch registers, it consists of a minimum number of instructions. The Bootstrap program is limited in that it can only load short programs. Longer programs require a second loader program, the Absolute loader. In summary, the Bootstrap loader's function is to bring in the Absolute loader program. The Absolute loader, in turn, brings in any paper tape program that we may wish to input. Now, let's take a look at how the Bootstrap program is loaded into memory. First, the Bootstrap is keyed in at the PDP-11's console. In an earlier study unit on the console, the switching sequence for loading the Bootstrap program was explained. The following discussion is based on the assumption that we have loaded the Bootstrap through the console. Do you recall where our Bootstrap loader is stored? The Bootstrap loader is composed of 14 instructions. Each instruction is assigned an address that is always in the highest 4K of memory. Therefore, the 2 most significant octal digits of the instruction's address are selected according to the memory size of your computer. For example, if your computer has 4K of memory, the 2 most significant octal numbers for each instruction's address are 0, 1. Therefore, the location of the first instruction in the Bootstrap program is 017744. On the other hand, if you have 8K of memory, the 2 most significant octal numbers for each instruction's address are 03. Therefore, the location of the first instruction is 037744. As you can see, the memory size determines the 2 most significant address digits for each instruction. After toggling in our Bootstrap program, the Absolute loader paper tape is inserted into the high-speed paper tape reader. Then, we input the starting address of the Bootstrap loader, which is toggled in through the console switch registers. The load address and the start switches are then pressed to initiate execution of the Bootstrap program. Note that the Absolute loader tape consists of 2 elements or sections, a leader section, which is then immediately followed by a program section. Each time the leader code is read from the Absolute loader tape, the processor completes 1 loop of the Bootstrap program. This leader code has no effect on our Bootstrap Loader program. The processor simply waits until it encounters the first data byte on the Absolute Loader tape. When the paper tape reader reads the first data byte of the Absolute Loader program, the Bootstrap starts transferring the Absolute Loader into successive memory locations. Each time the Bootstrap Loader loops, a byte of information is read and transferred into memory. As the Absolute Loader is stored in memory, a portion of this program overlaps or overlays the beginning of the Bootstrap Loader. As a result of this overlay, the leading section of our Bootstrap program is modified. The modified Bootstrap program causes the processor to break out of the loop when the last instruction in our Absolute Loader program has been stored in memory. The program counter then branches to a point in the Absolute Loader program. From that point, a portion of the Absolute Loader program is now executed. This restores the Bootstrap program to its original keyed-in condition. After the Bootstrap program has been restored, the Absolute Loader jumps back to a halt instruction. At this time, any one of the paper tape programs can be loaded into memory through the paper tape reader simply by pressing the Continue switch. Before we go on, let's review the basic purpose of the Bootstrap program. Remember, the Bootstrap Loader brings in the Absolute Loader. However, we must first enter the Bootstrap Loader through the console keyboard. Next, we place the Absolute Loader program into the paper tape reader. Then we start the CPU at the beginning of the Bootstrap Loader program. The Bootstrap Loader now reads the Absolute Loader tape and stores it in memory. The Absolute Loader is stored in memory a byte at a time. The read operation halts when the entire Absolute Loader has been transferred into memory. Now let's take a look at the Bootstrap Loader program. We'll begin our discussion with an overview of the major steps in the program. When the Bootstrap Loader is started, it first loads General Purpose Register 1 with the address of our Input Device's Control and Status Register, or CSR. This input device is usually either a teletype or high-speed paper tape reader. General Purpose Register 2 is then loaded with an address displacement. As we will see later on, this address displacement is used to calculate the storage address for the Absolute Loader program. Next, the Bootstrap Loader enables the paper tape reader, allowing it to read in a byte of information. Now that we have enabled our paper tape reader, we have to wait or loop until a byte of information has been read. When the byte is available, the Bootstrap transfers it into a memory location. This memory location is determined from the address displacement that we previously loaded into General Purpose Register 2. Next, the address displacement is incremented. Consequently, when another byte is read from the Absolute Loader tape, it is transferred into the next memory location. If the reader is not reading the last byte on the Absolute Loader tape, the program loops back and places the incremented address displacement into General Purpose Register 2. The cycle is then repeated until the reader is at the last byte. After the last byte is read in, the Bootstrap program branches to the Absolute Loader program. The Absolute Loader program then restores the Bootstrap Loader to its original keyed-in configuration. We have seen how the Bootstrap Loader is used to deposit the Absolute Loader program in memory. Now, let's look at the actual instructions that make up the Bootstrap Loader. Here are the 14 instructions that make up the Bootstrap Loader. It looks complicated, but don't be concerned. We'll step through the program instruction by instruction. We'll load the Bootstrap into a computer with 4K of memory. Therefore, the two most significant octal numbers for each instruction's address is 0, 1. Also, for this explanation, we will use a high-speed paper tape reader. As a result, location 017776 contains the address of the high-speed paper tape reader control and status register. We're now going to take a more detailed look at the Bootstrap program. Don't bog down in the explanation. After you've finished this unit, you may go back and cover the more subtle points you may have missed on the first pass. Okay, let's jump into the Bootstrap program. We'll begin our discussion with a closer look at the Bootstrap Loader flowchart that we talked about earlier. The Bootstrap Loader first loads General Purpose Register 1 with the address of the input device's control and status register. Let's see what instruction is used to accomplish this. We start the program by using a move instruction to transfer the address of our input device into register R1. This move instruction is stored in location 017744. To implement this move instruction, addressing mode 6 is used in combination with register R7. As you remember, this is called relative addressing. Remember, with relative addressing, our address is calculated from two components. One of these components is an offset of 000026. This offset follows the instruction. The other component is our updated PC, which contains the value 017750. Thus, we have calculated the relative address of a memory location. This is the last of the 14 Bootstrap locations. It contains the number 177550. This is the address of the high-speed paper tape reader control and status register. Thus, the address of the paper tape reader control and status register is moved from location 017776 to general purpose register 1. In other words, the processor now has the address of the input device's CSR that will be used to read in the Absolute Loader program. Looking again at the Bootstrap Loader flowchart, we see that the next step is to load General Purpose Register 2 with an address displacement. Notice that to transfer the address displacement, we use a move instruction. This is implemented in mode 2 through register 7. Therefore, the source operand immediately follows the move instruction. Our source operand of 352 is moved directly into General Purpose Register 2, since the destination location is coded as Mode 0, Register 2. Hence, we have stored an address displacement of 352 into Register R2. The address displacement can also be developed from the information contained in the mnemonic column. However, you will need some additional information to understand this. The word loop that precedes our move instruction is nothing more than a label. It identifies the location of this move instruction. The symbol that follows the opcode MOV should be familiar to you. It signifies the immediate addressing mode. In other words, mode 2 combined with register 7. The next symbol is a dot or period. This is a convenient way of representing the address of the current word or byte. In this case, the address is 017750. The constant load, which is defined elsewhere as 017400, is subtracted from this address. The result of this subtraction is 350. We finally add 2 to this result, giving us our address displacement of 352. Thus, we have used a move instruction to transfer our address displacement of 352 into General Purpose Register 2. Next, we have to enable the paper tape reader so that it can read in a byte of information. How is this accomplished? Address 017754 contains an increment instruction that calls for addressing mode 1 using register R1. General Purpose Register 1 contains the address of the high-speed paper tape reader's control and status register, which is 177550. The control and status register is currently clear. However, the increment instruction inserts a 1 in the least significant bit position. As we have already noted, this is the reader enable bit. When this bit is set, the reader proceeds to read 1 byte from the Absolute Loader tape. Now the Bootstrap Loader must wait or loop until the byte is read and assembled in the paper tape reader's data buffer register. Let's look at the 2 instructions that are used to implement this loop. These 2 instructions generate a loop condition waiting until a byte of information is ready to be transferred from the reader data buffer register into memory. The test byte instruction, TSTB, monitors the status of bit 7, which is the done bit in the reader control and status register. When this bit is set, a character is available in the reader DBR. However, bit 7 is also the sign bit for the lower byte. Therefore, the test byte instruction sets condition code N according to the contents of the reader's CSR. When a byte of information is read, the done bit in the CSR is set. Because this is the same condition as having a negative number in the low byte of the CSR, the N condition code bit is set. The branch if plus instruction tests the state of the N bit and causes a branch back to 017756 if N is clear. When a byte has been read, N is set, and we fall through the branch and go to the next instruction. Thus, we have set the done bit and dropped out of our loop condition. At this time, a byte of information is assembled in the DBR. We now take the byte stored in the DBR and move it into a memory location. This move byte instruction transfers the information from the reader DBR into memory. The instruction's source location is developed from the contents of General Purpose Register 1. Remember, R1 originally contains the address of the reader CSR. Therefore, when we add 2 to the value stored in R1, we produce the address of the reader's DBR. The destination address is developed from the contents of General Purpose Register 2, which is added to a constant, load 017400. In this example, General Purpose Register 2 contains our address displacement, which is equal to 352. Thus, load and 352 are summed to give 017752. This is the address of the memory location where the information from the DBR is to be stored. Thus, 1 byte of data is moved from the reader DBR into memory location 017752. The address displacement for the next data byte is now incremented. Let's see how this task is accomplished. Loop plus 2 represents the location that is going to be incremented. This location contains our address displacement. As you can see, the increment instruction is in the relative addressing mode. Therefore, the contents of the next location, which in this case is a -22, is added to the updated PC. The sum 017752 is the address of the location to be incremented. Looking again at the Bootstrap Loader program, we can see the result of this increment instruction. The address displacement stored at loop plus 2 is incremented by 1. The last instruction in our Bootstrap program is an unconditional branch returning us back to the beginning of the program. As you remember, an unconditional branch is an octal 400 plus the offset. If we subtract 400 from 765, we have an offset of 365. This is a negative offset, the 2's complement of which is 13. This causes us to repeat our read and storage operation. Counting back 13 words from the program counter, which is at 017776, we return to location 017750 to repeat the Bootstrap program until we read in our last byte of information. If we are reading in the last byte of information from our paper tape, we now branch to the Absolute Loader program and restore our Bootstrap Loader program. We have just finished covering the Bootstrap instructions. At this point, we recommend that you do not take a break, but go directly to the next section of this unit, running the Bootstrap.